In stats, we picked up where we left off with this auto pollution problem. And we had this conclusion. Let me change colors so I can point it out. So this was the interval we constructed in the last video. And look at part B. It says the EPA sets a limit of 1 gram per mile for average emissions, nitrogen oxide emissions. Are you convinced that this type of engine violates the EPA limit? Yes, we are convinced, because that entire interval is greater than 1. If even just a 0.999 comma 1.37 had been the interval, like if 1 had barely been inside the interval, we would have actually said no, because that means it's possible, like there's a slim chance that the true mean would be at one end of it. But since the entire interval, that's crucial right there, is greater than 1, that's why we can say yes. Make sure you back it up with context and your level of confidence. With 95% confidence. We believe this type of engine is in violation. All right, moving on. Hope you have a calculator for this next part, or just watch very, very closely. By the way, we're in this handout right here. If you didn't know, we're talking about the t distribution and t intervals. So hit pause and read through this problem. We are estimating the true mean tension in screens produced on this day, or on a day. That doesn't really matter. They took a random sample. That's good. But 20 is bad. So a week ago, 2 weeks ago, we talked about proportions. And we had to do the large counts test. That's not this case. This is a mean problem. For means, n needs to be greater than 30. Here, I'll scroll to it. It talks all about it. Maybe hit pause and read number 3. If the population is normal, the sample doesn't have to be large. It doesn't matter. If the sample is large, larger than 30, the sampling distribution will be normal. If the sample is smaller than 30, this is our situation right there in the middle of that paragraph, then we need to look at a graph to determine if it looks normal. So n is 20, obviously smaller than 30, that's bad. But look, conveniently, we have a graph to look at. But the graph looks, you could say a variety of things here. You could just say it looks normal, approximately normal. I've seen many textbooks really emphasize that it looks symmetric with no outliers, because sometimes it won't look perfectly bell-shaped. So I'm going to say symmetric with no outliers. That's more important because the t-distribution is really powerful. Like, it can handle some variability and not a perfect bell shape. And problems would be if we have outliers or a strong skew. But it's symmetric, no outliers. The t-distribution can handle it. Distribution is approximately normal. So that's worst case scenario. In the end, they just want to do some stats. So they're going to find a way to cut a corner and do it. Last thing for the condition is the sample needs to be smaller than 10% of the population. We have no idea what the population is, so we're just going to assume it's true. I mean, this is a production company. They're producing all kinds of things. I bet 20 is smaller than 10% of all they produced. We hope. All right, next part, we need a calculator because we have no idea what X bar is and we have no idea what S is. We do know degrees of freedom. We know that's 19, n minus 1, but we need to type all that in. So if you've forgotten how to do that, you go to a spreadsheet. So it's this bottom middle button with the grid. You open a spreadsheet, you need to name your column. I named it tension, and type in all the data. And pull your cursor back up to the top because we're about to do some calculations in the spreadsheet. All right, hopefully you got it typed in. Menu, stats, confidence intervals. I know it's a confidence interval, by the way, because it asked for one, a 90% confidence interval. I want to do a t-interval because we do not know sigma. I'll make that note on the paper. We do not know sigma. We're just working with a sample standard deviation. That is the main reason. I do not know what X bar and S are, but I do have a list of data values. So, okay, let's type in tension. And they asked for a 90%. Hit OK. And we have our interval right here. We have our mean. We have our standard deviation. We're good to go. So let's copy down all the stuff. Our interval is 288.224 up to 312.876. And now you just need to conclude. We have 90% confidence. That the true mean tension in screens produced on this day is within 288.224 and 312.876. All right, moving on. Oh, I didn't say it. Right here, I'm going to make a note. using T, not Z, because we do not know the value of sigma, population standard deviation. We only have S, sample standard deviation. For that reason alone, we choose T, not Z. No other reason. Just that reason right there. All right, moving on. Almost done with this handout. We have one more question, and it's a sample size problem. I'm going to zoom in a tiny bit. So they are checking cholesterol in monkeys, and maybe they're going to test some kind of cholesterol drug or something. They want to be within 1 milligram per deciliter correct. That is the margin of error. All right. They want it done at 95% confidence. And what else? They say we have a standard deviation. I'm going to hold off on using the symbol and just say standard deviation is, we're assuming 5. What is the minimum number of monkeys needed to meet those requirements? So here's the problem. Whoops. Here's the problem. Here's our T interval. And remember, this is the margin of error. That's an equation. That's on the first page of this handout. Or I think it's the second page, sorry. The X bar piece, this piece over here. The ME part that I just wrote, that's kind of implied. So I know what ME is. I could plug 5 in for S, but I hope you're stuck right here. T is dependent on N, right? We can't even use it. Cannot use T. Therefore, we have to make do. We have to start somewhere. Think of it that way. It's not a perfect scenario, but I'm trying to do some research, so I'm just going to use Z. This isn't a perfect scenario. You're just trying to get a approximate number of monkeys so that you can hopefully be within 1 milligram per deciliter. And we can't use T because of that reason up there. I'm looking for N, and T is dependent on N. No deal there. So because it's 95%, I flip to table B, look at the very bottom, and I see 196. Let's plug into my formula. Whoops, not equals. And we just need to solve for N. So let's divide both sides by 196. Some people go in different order. You could cross multiply. You could do a few things. I like to square everything. That's just me. And then I need to multiply both sides by N. To get it out of the denominator. Then just divide by that horrible fraction. And we get 9604. So we're going to say at least 97. All you have to show are these two things. You can go all calculator if you want. Just write those two things down and you're good to go. The very bottom is this huge assumption that statisticians make, and it's just a worst case scenario. Once again, they are trying to do research and they need a starting point. So what if there are no previous studies and we don't have a guess on standard deviation? Now what do? They had this idea, well, what if we made we knew an approximate range of the data, like what values we expect it to fall within? So one way would be to just take the range and divide by 4, and you could use that. So that's like a worst case scenario. Doesn't get any worse than that, I don't think. And then you could proceed. So that's it. See you later. Bye.